Welcome everyone. Today I'm excited to present a revolutionary perspective in cosmology, the redshift reset theory. This theory challenges traditional assumptions about the universe, particularly the nature of redshifts, planetary formation and cosmic structure. It offers a compelling alternative to the expanding universe model by proposing that the evolution of quasars, galaxies and planetary bodies follows a structured quantized process rather than a chaotic random one. Over the course of this presentation, I will walk you through key discoveries that support this theory, from planetary expansion to quantized redshift values and exoplanetary correlations. These ideas build on the pioneering work of the astronomers Halton Arp, Tifft and K.G. Carlson, whose observations have consistently challenged mainstream interpretations. Let's begin by exploring the fundamental overview of this theory. The redshift reset theory began with Dr. Halton Arp's observation that quasars are not the distant objects conventional astronomy says they are. Arp showed that quasars are physically linked by plasma bridges to galaxies, from which he hypothesized they were ejected, and that they gradually evolve into galaxies as their redshifts decrease. Along with another astronomer, Professor Jayant Narlikar, he proposed that this transformation is driven by a fundamental process, the incremental increase in subatomic particle rest masses over time. These increases occur in quantized steps, meaning that matter gains atomic rest mass at discrete intervals rather than in a continuous smooth fashion. The huge discrepancies in redshifts between galaxies and quasars are a consequence of this process. The higher redshifts of quasars are a result of lower rest mass electrons emitting lower energy photons. Their lower energy results in the shifting of the photon's emission spectrum towards the red end of the spectrum. As galaxies evolve, their redshifts continue to decrease by smaller and smaller intervals, reflecting smaller and smaller increases in the rest mass of the electrons and other subatomic constituents of atoms. This process extends right down to the planetary level, with small increases in rest mass causing planetary expansion. This concept has profound implications, affecting not just the large-scale structure of the universe, but also planetary formation, geological processes, and even mass extinction events on Earth. Rather than a universe dictated by random expansion, we see a structured, predictable evolution of cosmic objects. The work of Arp, Tifft, and K.G. Carlson supports this model by providing observational evidence of systematic patterns in redshifts and mass accumulation. Let's now examine one of the most striking implications of this theory, the expanding nature of planets and how this may have influenced prehistoric life. To start with, a fundamental question arises when we look at Earth's prehistoric past. How could dinosaurs grow to such immense sizes in the gravity we experience today? According to the square cube law, as an animal increases in size, its mass grows cubically, while its skeletal strength only grows squared. This means that extremely large land animals should struggle under Earth's gravity today. Yet fossil evidence shows that many massive dinosaurs moved with agility, indicating that Earth's gravitational pull was once weaker. This suggests an extraordinary possibility. Earth's mass has increased over time, leading to stronger gravity. This aligns perfectly with the redshift reset theory, which proposes that planetary bodies gain mass in discrete steps. This mass increase hypothesis is further reinforced by fossil evidence showing a systematic decrease in size among various species over geological time. Gigantic dinosaurs, insects and plants were far more common in earlier periods, whereas their modern descendants are relatively smaller. Could this be a direct consequence of a gravitational increase caused by gradual planetary mass accumulation? This observation suggests that planetary bodies do not remain static over time. Instead, they grow, shift, and develop, potentially triggering climate shifts, atmospheric changes, and evolutionary adaptations along the way. One of the predictions of the redshift reset theory would be that sudden increases in planetary mass occur over relatively short periods of time. In support, Miller and co-workers published a paper in 2019 showing the radiocarbon dating of dinosaur bone collagen from at least 24 different samples. The dating produced ages as recent as 22,000 years ago. whereas conventional science tells us that dinosaurs went extinct 65 million years ago. But this wasn't the only line of evidence. It was underpinned by one of the most controversial discoveries that challenged mainstream paleontology, and that is the presence of preserved organic material in dinosaur remains. Researchers such as Dr. Mary Schweitzer have discovered soft tissues, proteins, and even DNA fragments within supposedly ancient bones. This further supports the idea that Earth's mass, and consequently its gravitational field, has changed significantly over relatively short time periods, much shorter than the hundreds of millions of years posited by conventional paleontology, resulting in the reshaping of ecosystems and leading to the decline of larger organisms. Beyond scientific dating, there is another intriguing clue that suggests dinosaurs may have persisted far more recently than mainstream models suggest. Ancient cultures across the world have depicted remarkable illustrations of dinosaur-like creatures, often with a level of anatomical accuracy that would be impossible without direct observation. Petroglyphs in Utah, Cambodia and Kuwait clearly resemble long-necked sauropods and other prehistoric reptiles. Could these depictions indicate that early human civilizations coexisted with these creatures, or at least had knowledge of them through oral histories? If we accept that planets regularly undergo periods of expansion, then is there any further evidence for such an assertion? One prediction is that planets might destabilize or even explode after exceeding the critical size or mass threshold. As the subatomic particles of these planets accumulate rest mass in quantized steps, they may hit a tipping point that causes radial expansion, surface rupture, or loss of equilibrium. Evidence of such disruption might be found in the form of asteroid belts, planetary debris rings, and irregular moon distributions, potentially remnants of catastrophic planetary events, all of which can be found in our own solar system and in exoplanet systems. This hypothesis is further supported by the Fulton radius gap described in 2017 by Fulton and colleagues. Exoplanet surveys show a distinct gap in planets with radii between approximately 1.5 and 2.0 Earth radii, marking a transition phase where planetary processes seem to change. The mainstream explanation attributes this to photoevaporation, where high-energy radiation strips smaller rocky planets of their atmospheres. However, this slide raises a broader question. If planetary evolution occurs in discrete steps, could this gap also reflect an inherent instability in planetary mass accumulation? Exceeding critical mass thresholds could result in catastrophic failure, explaining the observed absence of planets within this size range. However, gas giants, which tend to be greater than 2 Earth radii and are obviously less rocky, escape this evil fate. Additionally, the phenomenon of single-planet exosystems provides further potential evidence of planetary instability. In such systems, which constituted over 70% of known exosystems, the one remaining planet is often a close-orbiting, tidally locked gas giant. This could suggest that the other planets in these systems have either been lost due to orbital instabilities or perhaps exploded or disintegrated under mass-related pressures. Finally, debris rings found around some exoplanets might represent the aftermath of these destruction events. These rings could consist of material left behind by planetary fragmentation or rejection events, providing further clues to these dramatic processes. The idea of planetary disintegration is not new. Researchers like Michael Ovenden and Tom van Flandern proposed that a rocky supersized Earth-like planet once existed between Mars and Jupiter, which later exploded, leaving behind the asteroid belt. Evidence for this event includes the unusual orbits of Mars moons, the asymmetrical surface of certain planetary bodies, and widespread deposits of water and carbonaceous meteorites throughout the solar system. Gas giants like Jupiter and Saturn in our solar system host large numbers of moons, some of which are thought to be captured bodies or remnants of the explosion. One of the underlying principles of the redshift reset theory is that planetary expansion must occur in quantized steps as atomic rest masses increase. In support, one of the key observations from Dr. Halton Arp's work was that planetary masses and orbital radii align with integer powers of 1.23, as is shown in the next two slides. This slide highlights Arp's discovery, showing that planetary masses within our solar system align with integer or half-integer powers of 1.23. This astounding result suggests a structured and quantized process underlying planetary formation and growth, possibly governed by a deeper cosmic principle. The table demonstrates how dividing planetary masses by successive powers of 1.23 produces results remarkably close to whole or half-integer values. This apparent mathematical regularity challenges conventional models of planetary evolution and hints at an organized framework linking mass accumulation to orbital mechanics. Could this pattern reveal a universal law shaping celestial systems? This slide is a continuation of the previous slide and highlights Arp's discovery, showing that planetary orbital radii in our solar system, in addition to their masses, also align with integer half-integer powers of 1.23. The divisibility of 1.23 into the masses and orbital radii of the planets and moons of our own solar system to give integer exponents is an utterly outrageous correlation. The far-reaching implications are equally shocking. How is the divisibility maintained? Do the masses and orbital radii of the solar system planets somehow keep lockstep? What might this mean for us here on Earth? What could be the possible mechanism behind it if it's true? The immediate reaction is to think it must just be a coincidence. But is there any way of checking if it's a fluke? The answer is yes, there is a way. In Dr. Arp's time as an astronomer, exoplanets were just being discovered. Currently we know of thousands of exoplanets. It must by now have become obvious that the masses and orbital radii of exoplanets allows us to test Dr. Arp's finding of the divisibility of integer powers of 1.23. If it turned out to also be the case for exoplanets, then it would provide virtually bomb-proof evidence for their lockstep increases in mass, tending towards divisibility by integer powers of this factor. In my previous book, A New Vision, I did in fact carry out such an analysis. The method I used was fully described in that book. Briefly, it involved dividing the masses of exoplanets by powers of a range of numbers, called base numbers, obviously including 1.23, and seeing whether the powers turned out to be integer values. The remarkable results of this analysis are summarized in the next few slides. Here we analyze single planet exosystems, where a lone exoplanet orbits a host star. What we find is astonishing. The masses and orbital radii of these exoplanets align precisely with integer powers of 1.23. This is not an arbitrary coincidence. As well as supporting Arp's findings for our own solar system planets, it also supports the contention of the redshift reset theory, that planetary formation follows a quantized structure, much like what we see in atomic physics. Next, we turn to multiplanet systems, where several planets orbit the same star. Here again, we find that planetary masses follow a distinct pattern, clustering around values that align with integer multiples of 1.23. This is significant for several reasons. It implies that planetary formation is not a random accretion process, but a structured stepwise evolution. It suggests that planetary systems across the universe are governed by the same fundamental rules, reinforcing the idea of a universal quantization principle. Despite the difficulty in measuring exoplanet masses, the fact that we observe these structured patterns points to a deeper underlying cosmic law. Not only do planetary masses align with quantized values, but the orbital radii do as well. This means that the distance of exoplanets from their host stars are not random, but instead follow a structured numerical relationship with 1.23. This mirrors what we see in our own solar system, where planetary distances appear to be arranged in structured intervals. This suggests that planetary formation obeys a universal law governing both mass accumulation and orbital positioning. If this pattern is real, and the data strongly suggests it is, then it provides an entirely new perspective on planetary formation, one that aligns with the quantized mass evolution proposed by the redshift reset theory. So, we've established that planetary masses and orbital radii align with integer or half-integer powers of 1.23. But why 1.23? What is so special about this number? The answer ties in with redshift quantization, implying a fundamental order to the universe. As I will show over the next few slides, Dr. Arp and other astronomers such as K.G. Carlson and William Tifft demonstrated that the redshifts of quasars and galaxies are not continuous, but instead follow periodic steps dictated by 1.23. We start with one of Halton Arp's most significant discoveries, that quasars are often physically connected to galaxies by matter bridges despite their vastly different redshifts. This observation is at the core of the redshift reset theory, for if quasars and galaxies are physically linked, then the large differences between their respective redshifts, often in the order of several magnitudes, cannot be due to the conventional paradigm, i.e., that the high redshifts of quasars are due to their much greater distances, which is of course the central hypothesis of the Big Bang theory. Arp's heretical observation that quasars are often linked to galaxies was proven over and over again and published in mainstream astronomical journals, often after much delay and obstruction from his more conventional colleagues. In the end, it cost him his job at the famous Mount Palomar Observatory, where he was denied any further time on the telescope there. After that, he moved to the Max Planck Institute in Germany and continued his work, publishing 3 books which can be found in the references at the end of this presentation and are still available on Amazon. But not only did Arp demonstrate that galaxies and quasars were linked, he also showed that quasars are often found aligned along the minor axes of galaxies, a prime example of which is shown in the next slide. As well as being aligned, Arp discovered one of the most compelling pieces of evidence supporting the redshift reset theory. This is the observation that quasar redshifts decrease with the distance from their parent galaxies. Again, this challenges the conventional view that quasars are the most distant objects in the universe. Instead, Arp proposed that quasars are ejected from galaxies and gradually evolve into normal galaxies over time. When we examine galaxies that have associated quasars, we consistently see a pattern, as is shown by the example on the slide. Quasars closest to the galaxy have higher redshifts, whereas quasars further away from the galaxy have lower redshifts. This means that as quasars move away from the central galaxy, their redshift values systematically decrease. If redshifts were purely a measure of distance due to cosmic expansion, this pattern should not exist. This observation strongly supports the idea that quasars are young, recently ejected objects, not distant relics from the early universe. But what might the decreasing redshift pattern of the quasars represent if they are not related to distance? The answer lies in a groundbreaking idea proposed by Halton Arp and Jayant Narlikar, the variable mass hypothesis, VMH. The VMH proposes that the redshift of an object is not due to its recessional velocity, as assumed in the expanding universe model, but is instead a result of its atomic particles having lower intrinsic rest masses. In a young quasar, the electrons and protons that make up its atoms have a lower rest mass compared to those in older quasars and galaxies. When these low mass electrons emit photons, the emitted light has a longer wavelength, meaning it is more redshifted. Over time, as the quasars gain mass, the rest mass of its atomic particles increases and the emitted light becomes less redshifted. This provides a natural explanation for why quasars have high redshifts and why their redshifts decrease as they evolve into galaxies. The diagram on the slide represents a visualization of the concept. On the left-hand side, we have a normal mass atom where an electron emits a photon at a typical energy level. On the right-hand side, we see a reduced mass atom where the electron emits a photon of lower energy, which is therefore more redshifted. The key idea here is that in young, newly ejected quasars, all atoms have lower rest mass, causing their emitted light to be intrinsically redshifted. Then, as the quasars evolve into galaxies, the rest mass of the subatomic constituents increases, and this is reflected in their decreasing redshifts. But there is another amazing aspect to all of this. Not only do redshifts of quasars decrease with the distance from their parent galaxy, Halton Arp and several other astronomers discovered that quasar redshifts fall into distinct periodic intervals, meaning that the redshift values of quasars increase and decrease in regular steps rather than forming a smooth, continuous distribution. What's even more remarkable is that these redshift periodicities are interrelated by the scaling factor 1.23, the same numerical pattern we observed in planetary mass and orbital radii distributions. This connection hints at a universal quantized process affecting everything from the smallest particles to the largest cosmic structures. The specific mathematical progression based on the factor 1.23 is referred to as Carlson's formula, discovered by him and published as long ago as 1971. See reference 16. Basically, each preferred redshift can be obtained by multiplying the previous one by 1.23, demonstrating that quasars evolve in quantized steps rather than continuously. Using this formula, Carlson derived a series of preferred redshift values for quasars, as shown at the bottom of the diagram. These values correspond almost exactly to observed quasar redshift peaks in large-scale surveys. In other words, when astronomers plot the redshift distribution of quasars, they find peaks precisely where Carlson's formula predicts them. Redshifts do not form a continuous spread, but instead occur at specific regularly spaced intervals. The implications of this are profound. Quasars appear to be ejected from galaxies, and their redshifts decrease over time as they evolve into galaxies themselves. This suggests that mass accumulation is occurring in discrete quantized steps, affecting the fundamental properties of matter. If quasar redshifts follow this structured periodicity, we must ask, do galaxies exhibit the same behavior? The answer is a resounding yes. Astronomers like William Tifft and Halton Arp demonstrated that the redshifts of entire galaxies also occur in distinct quantized steps rather than being smoothly distributed across space. Tift's work showed that galaxies exhibit redshift periodicities of 72 kilometers per second, forming discrete bins rather than random values. This finding is deeply problematic for the Big Bang model. If the universe were truly expanding at a uniform rate, redshifts should be randomly scattered rather than falling into clear-cut steps. Instead, the quantized nature of galactic redshifts suggests that mass accumulation and cosmic evolution follow structured periodic changes, reinforcing the core ideas of the redshift reset theory. However, whereas the quasar redshift quantization pattern is dictated by simply multiplying the previous value by 1.23, the relationship of 1.23 to galactic redshifts, which are several orders of magnitude lower than quasar redshifts, is slightly different. Arp asked what power would 1.23 have to be raised to in order to give the galactic quantization period of 72 kilometers per second. The astonishing result was that this power corresponds to 6 decimal places to the anomalous magnetic moment of the electron. Why is this such a big deal? It so happens that the electron magnetic moment is inversely proportional to its rest mass, as shown by a paper published by Bowen and Mulkern in 2015 and proven independently by myself, as shown in my book A New Vision. Their paper is also referenced at the end of this presentation. This means that as an electron's rest mass increases, its magnetic moment decreases, and vice versa. So, the decrease in galactic redshifts, as for quasars, is due to their electron rest mass increasing, which itself is a consequence of their magnetic moments decreasing, and the quantized decrease in their magnetic moments is dictated by powers of 1.23. This also directly correlates with why planetary masses are divisible by 1.23. It's all down to the quantization of the magnetic moment of the electron by powers of 1.23. But what about all the other atomic constituents? Protons and neutrons, etc. Bowen and Mulkern provide a model in which these subatomic particles are formed from electrons and positrons. Please refer to their paper for further clarification. This slide just shows a simplified summary of what I've spoken about in the previous slide with respect to the correlation between redshifts and electrons' rest mass and magnetic moments. Please pause and take a look at it. Now, the final piece of the redshift reset theory was provided by William Tifft, a mainstream astronomer who, like Arp, started making discoveries that contradicted the conventional redshift equals distance paradigm. What Tifft showed was that galactic redshifts decrease over short periods of time as their constituent subatomic particles increase in rest mass. This is shown experimentally in the next slide. Tifft analysed the redshifts of 625 galaxies across multiple decades and found that their redshifts were decreasing over time. Tifft measured the redshifts of the galaxies in 1984 to 1988 and subtracted them from the redshifts measured for the same galaxies by Fisher and Tully from 1973 to 1977. As is shown, nearly all the redshifts had decreased in just over a decade, implying their subatomic rest masses had all increased. In his paper, shown in reference 11, he also showed the same pattern for other decades. In effect, this means that every time the redshift of a galaxy notches down a step, it is caused by a slight increase in the rest mass of the atomic constituents of the galaxy. In this respect, it would merely be a continuation of the steady gain in rest mass of the atoms of quasars as they evolve into galaxies. Cosmic objects never stop increasing in rest mass, but it's important to realize that such increases in atomic rest mass at each step of quantization are only a small fraction of a percent of the rest mass of an electron. However, as Professor Tifft showed, they do occur on a very regular basis. This brings us full circle back to the reason behind planetary expansions and the regular occurrence of extinction and level events, the decreases in the size of flora and fauna, the explosion of planets, and much more. It's all basically down to the quantization of the universe, and the quantization factor is 1.23. The redshift reset theory provides an evidence-backed alternative to the Big Bang model. Unlike the conventional view of a static mass universe, this theory suggests that mass evolves in predictable quantized steps. This structured growth process impacts not only redshift periodicities, but also planetary expansion, changes in gravity, and even mass extinctions throughout Earth's history. The evidence supporting this idea spans multiple disciplines, from astrophysical observations of quasars and galaxies to planetary science and paleontology. If mass truly evolves in quantized steps, it fundamentally reshapes our understanding of the universe, the formation of cosmic structures, and the forces driving planetary and biological evolution. The implications of this theory are vast, challenging long-held assumptions and opening new avenues for scientific exploration. Please pause for a moment and take some time to study the points on the summary slide. Finally, if you're interested in a deeper dive into the calculations, observations, and implications of this theory, I invite you to explore my books on Amazon, where these findings are presented in greater detail. There's also a website at redshiftsreset.com and a Facebook page, The Redshift Reset. Thank you for your time.